All right, so I'm going to record this. Just to let you know, if you have any questions, you can feel free to get on your mic and ask me a question, or if you want to put it on the chat, I will stop every so often to see if there's any doubts. So what we're going to do is continue our discussions about coordination chemistry. So this lecture is divided into two parts. The first part, we're going to discuss some of the basics of nomenclature of how we go about naming coordination compounds. And the second half of this lecture will focus on those factors that contribute to the thermodynamics of coordination compounds forming. So just a brief overview of what we've discussed leading up to this lecture. We finalized our discussions of acid-base theories, focusing at the end on the Lewis definition, which introduces us to different types of reactions that involve the formation of adducts. A subset of the Lewis definition is a hard-soft acid-base theory, which defines species based on their polarizability. And so this definition of how polarizable something is gives us insight as to what types of species will have a preference or a stronger affinity for one another. And this led us to then introduce coordination chemistry, in which we define a coordination compound as consisting of the interactions between a metal as a Lewis acid interacting with ligands as Lewis bases. And so as a way of providing you the insight as to what coordination chemistry is, I provided you the history of the contributions by Alfred Werner with regards to his experiments with cobalt complexes that really revolutionized the field, the way of thinking about what type of bonds can actually form. So what I would like to discuss today is this idea of how do we actually characterize the interaction or the binding of ligands to metals. And so one of the features to define is denticity. So at the root of this word is dent, which basically implies dental. This is the concept of basically how many atoms does a ligand bind to a metal or bind onto a metal. So it defines the number of bonds that a ligand can form. And what we use is a series of prefixes to distinguish the denticity of ligands. And so I provide you this table, which gives you the prefix and the corresponding number of coordinating atoms. And so just to give you just an overview, if you have one atom in a ligand able to coordinate to a metal, well, that ligand would be defined as monodentate. So that would be the terminology. Mono, where you have the prefix, and then dentate, referring to the denticity. And so if you have a ligand capable of coordinating at 2 atoms, well, that would be bidentate. 3 atoms would be tridentate. 4 atoms would be tetradentate. 5 atoms would be penta. 6 atoms would be hexadentate. And so this gives us an overview of how we can actually think about this idea of coordination. So to illustrate this, I want to give you just a cartoon representation. So let's imagine that we have a coordination number of 6. And so we're going to use this particular figure here, which defines something that is octahedral, in order for us to think about the denticity of ligands. So here I have the representation of ligands as something very generic, where I'm using X as the coordinating atom. So here I'm going to distinguish the ligand that I'm focusing on by using the letter A. So in this context here, by having this one atom coordinating to the metal center, well, that would define something that is monodentate. But then if we have a ligand that has 2 different atoms capable of coordinating to metal, and in this context it does, well, here then we have it serving as something that is bidentate. And so here then the visual of a tridentate ligand, something that's tetradentate, something that is pentadentate, and then an example of something that's hexadentate. Now, this is not to discard the possibility of perhaps a higher denticity, but these are the ones that are typically likely to form. And a very important thing is that when we're discussing a ligand that can bind at 2 or more sites, well, that refers to a ligand that is polydentate and more commonly referred to as a chelator. So you may be familiar with the terminology chelation therapy, which is an approach that's taken when there is toxicity associated with an excess amount of metals in a living organism. So chelation therapy is an approach that people take to try to minimize the toxicity associated with these metals. And so what I want to talk about a bit is what are the common ligands as far as some of the ones that we're going to be referring to when we discuss coordination compounds and breaking them down into certain categories. So here we're looking at monodentate ligands. So again, capable of binding at with one atom. And we're referring to those that have anionic capability. So, putting this into context, when we think about metals and ligands interactions, remember that the ligand is the Lewis space, so it's the source of electrons. So it's very likely that a ligand would be anionic as it has the pairs of electrons that can be provided to a metal to form a metal ligand adduct. And so here on the left, we have halides. And so I'm giving you just the common ligand names associated with them. But we have fluorine, which is an anion, is referred to as fluoro, as when it's coordinated to a metal. Um, the chloride referred to as chloro, the bromide referred to as bromo, and iodide referred to as iodo. Then we have those ligands that are very obviously not halides, but can coordinate in a monodentate fashion that would be characteristic of how halides would coordinate to a metal center. So again, you following the theme of something that is monodentate. So we have the cyanide ligand, which is referred to as cyano. And then we have the cyanato ligand, the derivative of that, the thiocyanato ligand, and the azido ligand. And then we have other very common anions, such as hydroxide, which is referred to as hydroxyl. When hydrogen becomes negatively charged to the hydride anion, we refer to as hydrido. And then we have here the nitro ligand. Another pretty common set of ligands that you can have are molecules that are neutral. And so here are some of the really common ones, such as the family of amines. So as you know, amines have a pair of electrons on the nitrogen. So that's the source of electrons that can coordinate to a metal center. So when the ammonia molecule coordinates to a metal, it's referred to as amine. And as you can see, that particular ligand, the spelling of it will have a double M, where then the derivatives of this particular molecule, such as this methylamine, as you can see, that spelling of the amine part is not retained, so you just have the normal spelling. So you have the methyl and then the one M there. We have dimethylamine and trimethylamine. So again, these are the series of amines and capable of coordinating through the free pair of electrons on the nitrogens. Then you also have the water molecule. As I briefly mentioned in our last lecture, solvents have the capability of interacting with a metal center. Water is an example of this with its free pair of electrons on the oxygen. When it coordinates to a metal, it will be we refer to as an aqua ligand. Then you have the carbon monoxide molecule that when coordinated is referred to as a carbonyl ligand. And the NO molecule is referred to as a nitrisol ligand. And then you have basically the family of ligands that are phosphorus-based, like the amines, in this case, the phosphine family of ligands, and just one example of them, the trimethylphosphine, where you have the free pair of electrons on the phosphorus group. So going from a classification of things that are monodentate, again, things that can coordinate typically at at one atom, here's an example of those type of ligands that fall into the category of chelators, so polydentate. And so what I'm going to refer to is the capability of them coordinating to a metal center and the types of rings they can form. So here you have an example of a molecule, oxalic acid, that when it coordinates to a metal center, it has a capacity of dissociating its protons, although that's not always a requirement. So you can have the example that you see on the right, where the protons are actually present. It really depends on the given solution that you're working with. But here, what I'm going to focus on is the coordinating atom. So we have coordination through these two oxygens. So that's basically the side where you have those acidic protons that are capable of dissociating. And so when it coordinates to the metal center, it's coordinating as an oxalato anionic ligand. And what you see here is the coordination that's facilitating the formation of a five-membered ring. So let's define what's constituting that five-membered ring. Well, you have the metal, then you have the oxygen, the carbon, and the oxygen. And so that's the components of the five-membered ring from the coordination of that particular ligand. Then you have here an example of a ligand, the acetylacetone. So this particular ligand has the capability of coordinating through its two oxygens, okay, using its their free pair of electrons. And so when they coordinate to the metal, as you can see in the figure on the right, in this anionic form, this is the acetylsonado ligand, this anion. And so here then you have a representation of coordination that forms a six-membered ring. All right, so let's focus on the constituents of that six-membered ring. Well, we have the metal, we have an oxygen, the carbon, the carbon, the carbon, and the oxygen. And so we have this feature here that's giving you that six-member ring structure. And so we're actually going to return to this idea of like the types of rings that certain chelators can form as an element that can provide for stability to these type of coordination compounds. All right, so we also have polydentate molecules, chelators, that can coordinate, and in this context, will coordinate and will basically be something that is neutral in their charge. So here's an example of a member of the amine family of ligands. So here, ethylene diamine, which is a chelator, as it can coordinate through the free pair of electrons on both of these nitrogens. And so when it coordinates to that metal center, well, the ethylene diamine itself is a neutral molecule. And so it retains that neutrality as it coordinates to the metal center. And you have here the formation of a five-member ring as it coordinates to that metal. Then here you have a representation of something also part of the amine family of ligands, diethylene diamine, which has a capability of coordinating in a tridentate fashion. So this is also a neutral chelator. And so what we have is coordination through the three nitrogens using their free pair of electrons. And so you can see the coordination to the right as a consequence of this interaction. And there's another thing that you can see are the types of rings that can form. So here you have a representation of, one type of ring that forms, which consists of a five-member ring. And then you also have another ring on the right side, which is also a five-member ring. All right, so these features that will be something that, again, I'm going to allude to when we're discussing more about the stability of these type of compounds. All right, so with that in mind, then, we have a sense of ligands and the charge state typically neutral or negative. And again, to emphasize, when we're talking about ligands, they are Lewis spaces and they provide electrons to the metal center. And the metal can be neutral in charge, but also very commonly can be cationic. And so there's something to think about in terms of defining the charge state of an overall metal compound. And so we talked very briefly in our last lecture about this idea of the primary coordination sphere, which is a sphere that defines the direct bonds between the atoms of ligands to the metal center. And we also talked about the secondary sphere, which has to do with what basically is interacting with the primary sphere. All right. So with that in mind, then, certain metal complexes can be charged. And so that's something that we take in consideration in terms of how we visualize a compound, but also how we refer to it in terms of naming. So when we're talking about charged molecules, what we do is we list the cation first, and then we list the anion. So keeping this in mind, then, we apply the following rules. And so these rules apply to both neutral and charged molecules. Okay, so just keep that in mind. All right, so the elemental formulation that is referring to the actual primary coordination sphere, well, that will be listed or presented to you in brackets. So that's actually showing you what is constituting the primary sphere, what are the ligands that are actually bound to the metal center. And so something like this, as you can see, what we're looking at here is we're looking at a platinum compound that has four amine ligands coordinated to it. And then what's affiliated with that primary sphere are two chlorides, right? So those two chlorides are constituting the secondary coordination sphere. So in this context, they're helping to balance charge. And so let's try to figure out how they're doing this. So in here, we have this platinum compound, and it has four amines coordinated to it. So that actually forms a square planar structure. And we're going to talk about this idea of the coordination geometries that can form as a consequence of coordination number. So we have this structure here. All right, so here we need to figure out a bit about the charge state of our molecule, but also very importantly about the metal center. So we need to have the context to understand this. So we have this primary coordination sphere, which is square planar, and it is interacting with the two chlorides, which, as I said to you, these are going to be they are part of the secondary sphere, and they're anions that are actually serving to provide for a charge balance, an overall net neutrality of, so a charge of 0. So if you have a charge here that's going to be overall 2 minus because of the two chlorides, then what that implies is that your primary sphere has a charge of 2 plus. So if that primary sphere has a charge of 2 plus, then we have an idea as to what's going to be the charge state of our metal. Because the amine ligands, well, these ligands are all neutral in charge, right? So they don't contribute anything to the charge. So what that would then dictate is that the charge of your metal has to be 2 charge, which is providing for the overall charge of the primary sphere. And again, that's going to be balanced by the presence of the two chlorides interacting with that primary sphere. Clear this up. And it's a bit just for clarity to show you that perspective. So that square planar platinum 2 compound. So when writing the name, the ligands within the coordination sphere are written before the metal and are listed in alphabetical order. So in this case here then, what we have for this particular molecule is that we have the platinum, and it's coordinated by 4 amine ligands, and then we have chlorides that are serving as counterions. And so this one's a very simple molecule to name because we only have one type of ligand coordinated to it. So in this case, and I am going to explain more as to how I go about naming this, but we list the ligand before the metal. So we list the amine. Okay, so the MMINE. We actually list the number of that ligand that we have. And so in a moment, I'll explain to you where that prefix is coming from. And then we list the metal with this associated oxidation state, in this case, the charge of 2 plus. And then we know the chloride. It's important to see here that I'm actually not specifying the number of chlorides, as it's apparent based on the actual information that's provided here with regards to the primary sphere coordination. However, you could write the number of chlorides. It's not something that I would personally deduct any points for, but it's something that's not required, given that the context clues will tell you that there should be 2 chlorides in order to balance the charge. Clear this up a bit. All right, so when we're referring to ligand names, so it depends on the type of ligand that we're focusing on. So obviously, if we're talking about monodentate ligands or chelates, how we go about using, specifying the name of the ligands, but also we're going to talk about how we specify how many of those ligands are present in the molecule. So here I provide you a table that lists the prefixes that we would use to specify the number of ligands that are coordinated to the metal center. So you will see in this table that we have 2 columns, one listed as A and one listed as B. And so it depends on the situation when we select a prefix from either the column A or the column B. So here we're looking at column A. And so it turns out that we use prefixes from column A when we're referring to simple cases. And obviously, what does simple cases mean? Well, we haven't even talked about anything really. So let's define A with regards to column B. So you choose prefixes in column B for ligands with names that already use prefixes from column A. All right, so here's where B is referring to things that are a little bit more, a little more complicated, but really not that complicated. So here's an example. We have a compound which has a cobalt metal and is coordinated by a chelator. And so En is a ethylene diamine, so that's a chelator. And in that name, it includes a prefix. And so in order for us to specify how many of that particular ligand is coordinated to the cobalt, we're going to need to use a prefix from column B. So let's look at just the example here. So that chelator, ethylene diamine, and there are two of them. So the way that we're going to refer to it is by choosing the bis from column B to refer to it. But then remember that we list all the ligands alphabetically. So here we actually have chloro. So we put the chloro first because alphabetically C is before E of ethylene diamine. And we also have to list how many chloros there are. And in the case here, chloro is something that's a simple case. So we will put the phrase di before it. So this is dichloro, bis ethylene diamine, cobalt, and then we specify the oxidation state, the charge of the cobalt, 3+. So another thing to note is that we will always use prefixes in column B when the name of a ligand begins with a vowel. So as an example, here we have this compound here, where we have 6 water molecules that are coordinated to the metal center. And so that water molecule, as I mentioned already, is referred to as aqua. And so aqua has a vowel that starts the name. So to refer to the 6 water molecules coordinated, well, we have to then use the term hexakis from column B. So it'd be hexakis aqua rhodium 3+, and that's referring to the oxidation state of the metal. Okay, so that's basically how we go about selecting the prefixes either from column A or column B to dictate how many ligands are coordinated to the metal center. Okay, so ligands are written in alphabetical order according to the ligand name. So here I'm emphasizing not the prefix. So it's according to the ligand name, and we'll have opportunities to practice that. And there are going to be some conditions that we also have to take into consideration, where if you have an anionic ligand, well, that would have an O as a suffix, so the O would end the name of that ligand. If you have a neutral ligand, well, the neutral ligand will retain its usual name. When you have coordinated water, as I already mentioned to you, coordinated water is referred to as aqua. And then coordinated ammonia, well, I've already referred to, that's referred to as amine. Right? This is just to note a few certain conditions where there'll be changes, possible changes to how you will refer to the ligand. All right, so let's do some practice here. So we have 2 compounds. Let's start off with the first one where we have a variety of ligands bound to that metal center. So here, let's note how many ligands are coordinated. We have this ligand, this one, and this one. So that means we have a coordination number 4 here. Okay, and so what do we have? So let's do this in the alphabetical order. So we have chloro, we have bromo, we have amine, and we have aqua. All right, so now we have those 4 ligands, and then we also have to specify the charge of the metal center. So here we can take a moment to identify what's neutral and what's anionic. Okay, so these 2 are neutral ligands. So they're not going to contribute anything to the overall charge of this particular compound. These 2 are anionic. They both have a charge of -1, okay? So keeping that in mind, we have -1 and -1. This overall molecule, because there's nothing as associated with it, will have a charge of 0. So what would be the charge of the metal then, with those ligands bound to it?
+2.
Yeah, so it'll be +2, okay? So that's +2. Okay, so also try to name that ligand. I'll tell you that molecule. How will we go about naming the compound?
Aqua, aqua, bromo, chloro, I don't know, I'm lost.
Well, you started off okay. So we have the names of this. Okay, let's clear this up a bit. So we have amine, aqua, bromo, chloro. So you put the A's, right? And so amine goes first. aquabromochloro, and then we'll list the platinum and then the corresponding oxidation state of 2. Okay. All right. So then the second one, well, here we're provided pretty simple compound because now we only have one type of ligand, and that's the amine ligand. So we don't have to do much in terms of listing the ligands. So we have the amine, and we know that we have 4 of them. And we also know that amine is neutral. Okay, so that's important. But we're given the overall charge of 2 plus. So if that particular compound has an overall charge of 2 plus, and the amine is not contributing to the charge, well, then that charge is coming from the actual metal. So that would be 2 plus. So then here, then, when we actually are going to write the name of this particular ligand, so we have to list how many of them, and there are 4, and that particular ligand starts with a vowel, so we have to choose a prefix from the column B that I provided you. So you're going to be given something like, I'll see if I can cancel that. So it's going to be tetrakis, amine, platinum 2. Okay, so it's a pretty simple one. So now, if the molecule, and I'm talking about the primary coordination sphere, is negatively charged, then the suffix ate is, we have to use it in terms of naming the actual metal. So we're going to apply the suffix to the name of the metal. Right. So let's look at an example here. So here we have this platinum compound, and so we have two types of ligands coordinated to it. We have the amine, and then we also have the chloroligand. Okay. And we know that we have 3 of those chloroligands bound to the platinum. We know that the amine is neutral in charge. And we know the chloro is anionic. It has a -1 charge. We also know that the primary coordination sphere has an overall charge of 1 minus. All right, so this is really important in terms of how do we go about defining this, because here we have the amine contributing 0. We have 3 chlorides, chloroligands, each with a -1 charge. So this would be 3 minus. So when we're thinking about this, we have an overall coordination sphere that's going to be 3 minus, excuse me, that's going to be 1 minus, where we have those 3 chlorides present. So in order for us to have a final charge of 1 minus, well, that dictates that the platinum has to be 2 plus. Okay, in order for us to have an overall charge of 1 minus. So we keep that in mind because it's the overall primary coordination sphere that is negatively charged. So when we're going to list the actual name, well, we list the amine first, as is the one alphabetically. Then we list chloro and the prefix tri to emphasize that we have 3 chloroligands. And then because the primary sphere is negative, well, we list the platinum, but we use the suffix ate to imply that this is coming from a negatively charged primary coordination sphere. And then we also list the oxidation state of 2 corresponding to that metal. So that's important. Keep in mind, if you have a primary coordination sphere that's neutral or positively charged, you do not change the suffix of the metal. But if the overall primary coordination sphere is negative, then you do. All right. So when it comes to naming metals in negatively charged molecules, then you have certain special names for certain metals. For instance, for copper, instead of saying copperate, what you would say is cuprate. For iron, instead of saying ironate, what you would say is ferrate. Silver is arginate. Lead is plumate. Tin is stannate. And gold is aurate. All right, so these are, they're not necessarily exceptions, they're the modifications to the name in order for you to apply the suffix when naming these compounds. So additional things that to note when it comes to the nomenclature is when you have certain isomers and how you can refer to the location of certain ligands. So here we have classical representation of a platinum to a square planar compound. And so you see that to the left, you have the cis arrangement of the ligands. Cis mean that the ligands, for instance, the chloro groups are they are neighboring one another, and the amines are neighboring one another. Versus the trans arrangement of these, where you have these nitrogens from the amines 180 degrees apart from one another, and then you have the chloro groups 180 degrees apart from each other. So these are isomers. And so we can use these terms as they apply in order to be able to dictate the geometric location of ligands. So the one to the left, we can refer to it as cis bisamine dichloroplanum 2. And so I just emphasize that that particular compound is known to be a potent anti-cancer agent, whereas the trans version of that compound is something that does not have that bioactivity. All right, so this is how we can use the terminology cis and trans in order to define the location of a ligand. And then you have certain cases where a ligand can actually facilitate bridging. And so here's an example where we have this dimeric compound, which has two cobalts. And so these two cobalts are bridged by two ligands. So here you have an amine, so in this case, an anionic version of it that's coordinating the two cobalt centers. So it's using its two free pair of electrons in order to be able to do that. And then you have hydroxide that's also playing that type of role as a bridge between these two metal centers. All right, so how do we go about trying to define this particular compound? And we also have to keep in mind the charge, right? We have an overall charge of 4 plus. We have a lot of these amines, which these amines are going to be neutral in charge, and then what's serving as bridges, well, these are anionic. So these are things that we have to keep in mind in order to then understand what's going to be the overall charge of the molecule and what will be the charge of the two cobalts. So it turns out that as far as naming this, so here we have to keep in mind the use of this particular prefix mu, as that helps us to dictate that there are ligands that are serving as bridges. And so in this case, then, we are distinguishing those two bridging ligands alphabetically, the amido, right, the anionic version of an amine, and the hydroxyl, well, mu amido, mu hydroxyl, and then we start to specify the coordination of the amines on the cobalt center. And remember, this is a dimer, so we have to break it down into its parts. So at each cobalt, we have 4 amines, so that would be tetrakis. The cobalt center is 3 plus, so if you do the math, you would see how each cobalt would actually be 3 plus. But because they have 2 of these units, it would be bis. Okay, so this is how we go about piecing it together, that we have the bridging amido, the bridging hydroxyl, 2 units of the tetrakis amine cobalt, and the corresponding oxidation state of the metal. And again, this is going to be overall a cationic species. Therefore, the name of the cobalt will remain the normal name of the metal. All right, so before I move on, are there any questions or doubts with regards to these basic rules for nomenclature? All right, again, if something pops up, you can feel free to get on your mic or to type into the chat. All right, so the next part of this lecture, we're going to focus on the number of things that contribute to the thermodynamics of metal ligand binding. So what are those things that are driving the formation of these compounds, that making them something that's quite favorable? All right, so here I'm giving you this perspective of metal ligand adduct formation with a very simple reaction expression. And we're looking at a reaction coordinate plot, which basically a reaction coordinate plot gives you a time profile of a reaction in progress. All right, so what does that mean? So we're looking at essentially the reaction of the metal and the ligand forming the adduct. So at the beginning, so this is basically in terms of time. So at the beginning, we start off with the reactants, in this case, the metal and the ligands, and we are looking at the relative energy corresponding to these two reactants. So that's why this is in terms of energy. And we see what happens then as they go through the process to interact in order to lead to the formation of their adduct, the metal ligand adduct. And so here we're just basically plotting this energy profile over time. All right, so let's try to distinguish the features here. So we start off at a certain energy level. Okay, so that energy level is here. And again, that is the net energy corresponding to the metal and the ligands in their free form, so not adduct form. And then we see that there is an increase in energy. Okay, so we see this increase in energy. And so that's a consequence of, transformations that are occurring as the metal and the ligand are coming together in solution. And so here the energy is increasing. So there's an actual energy barrier that's being overcome. And then once you overcome this energy barrier, then what you see then is that you decrease overall your system, the energy of your system, until you reach this point, this minimum here, that corresponds to the formation of the metal ligand. All right. So let's try to make sense of the different features here, because here we're talking about this energy barrier that you have to overcome. And then you're also talking about the energy difference from where you were at the start and where you were at the end. So let's clean this up. Okay. So we can look at this from two different perspectives. So one of the perspective is how fast this process occurs. So the way that we keep this in mind, we have this expression here where we have this equilibrium term, right? The forward arrow and the reverse arrow. So basically, that's indicating to us that we're looking at both the forward reaction and how fast that's occurring, and also the reverse reaction, the metal ligand adduct breaking up to give us the free metal and the free ligand. So, well, essentially here, this part of your reaction coordinate profile, your profile here, well, that is gauging the activation energy. So what do you need to, do as far as activating this process in order to facilitate the formation of this adduct? So that barrier there is basically then measuring the rate of how fast that forward reaction is going to go. All right, so we're looking at, in this context, the how fast or even slow the complexation event is. And the bigger this parameter is, so here this parameter is measured by delta G1. Well, the bigger that is, the slower the overall rate of the reaction is going to be. So that's why I have this expression here at the bottom, because that's basically the relationship that we're looking at, that activation energy barrier that needs to be overcome. So we can also look at it from the reverse process, right? The breaking up of the metal ligand adduct to give you your metal and your ligand. And here we have the measure of that activation energy barrier. And so that tells you how much energy needs to be overcome in order to break up that complex. And so that barrier also is a measure of how fast or slow that process is going to be. So it's again the same thing, the same premise. The bigger the barrier is, the bigger the delta G is, the slower the rate is going to be. And so later in the course, we're going to talk more about this idea of kinetics, because the idea of kinetics can be influenced by the exchange of ligands. And so that's something we'll talk about, this idea of ligand exchange and how fast or slow that's going to be. But the key thing that I want you just to focus on now is that from this reaction coordinate profile, we know what part of the profile corresponds to the rate of the forward and the reverse. But that's not going to be the actual focus of today. What we will focus on today are the thermodynamics of this process of metal ligand adduct formation. And so here then, we're going to be focusing on the equilibrium expression and our K expression, which is equal to the concentration of the metal ligand adduct divided by the concentration of metal and the concentration of the ligand. And so what are going to be those factors that are contributing to this? So as far as our reaction coordinate profile that is giving us insight into the thermodynamics, well, That insight is provided by that energy difference between the starting point, so the energy of our metal and ligand reactants, and then the endpoint of our metal ligand adduct. So what we were focusing on is literally that energy difference here. Okay, so this energy difference is telling us about the overall thermodynamics. And it also tells us whether the reactant or the products are being favored. Is there a question? All right. That tells us some insight about the whether one side or the other is favored. So in this case, what we're looking at is that at the end, the net energy is lower than the starting point. Okay, so we were here and now we end up over here. So from this perspective, then your system is lowering in energy, and that lowering in energy is a stabilization process. And so what that implies then is that this formation of the metal ligand adduct is something that's favorable because it's lowering the overall energy of the system. And so that barrier, this particular delta G, this Gibbs free energy of the difference between the products and the reactants, well, as a measure of stability. So the higher that difference is, right? So the lower, right? The lower the energy of the metal ligand adduct is, the more stable the complex is. Okay, so keep that in mind because that's going to be important to give you insight as to what is likely to form. All right, so as we're defining then the formation of metal ligand adducts, well, let's talk about a little bit with regards to the steps involved. And so here we're not going to get anything particularly in depth. I'm just going to define terminology in order for you to distinguish the steps involved in metal adduct formation, metal ligand adduct formation. And so we can look at this process as the affinity, how strong a ligand will bind to a metal center, and how we represent this in individual single steps or in multiple steps. All right, so we're going to first start off with single step metal ligand interactions. All right, so when considering a single metal ligand interaction, we treat the interaction as a single ligand addition, and that is regardless of whether the ligand, regardless of the denticity of the ligand. So whether the ligand is monodentate, bidentate, tridentate, and so forth, we're not actually factoring that in our definition of a single step process. All right, so because we're not factoring the denticity, we're going to retain this really simple expression here. Where we have a metal, we're adding in the ligand, and we get our metal ligand adduct forming. All right, so we have this equilibrium expression. So this is a one-step process because we literally have one metal and one ligand, and we get our adduct. So we get our K expression, which is, as I stated before, concentration of your metal ligand adduct divided by your concentration of metal and the concentration of ligand. So it turns out that this expression here, well, that's basically a formation constant. Okay, so what does that mean? Well, that means it's a measure of the strength of that interaction. It's also a stability constant. It's the same idea. So how strong this interaction is. And so as we've discussed in the course previously, the higher the value of K, the stronger the interaction of the product is. And so the drive towards the formation of product. But let's imagine then we interact with a second ligand. And again, we don't take in consideration the denticity of the ligand itself. So if we just focusing on a second ligand being added, and we're going to focus on this in a single step process. All right, so let's consider that. All right, so just to review, here is our expression for one ligand bound to one metal, and that's a one-step process. Okay. But then we already formed this metal ligand compound, and now we're considering a second ligand being bound. So here we have our metal ligand compound, and then here's the second ligand being bound. And that's going to give us this adduct of the metal with the two ligands bound. And that's why we're using this subscript 2 to imply that we have two of the ligands bound. So here, the expression that we have is also a single step expression because it's the expression for that one ligand binding to the metal center. And so here then, our K expression is such that we have the concentration of Ml2 divided by the concentration of Ml times the concentration of L. And so these are K expressions because K expressions denote single step processes. Let me write that here. All right, single step processes. And again, keeping in mind that we're not factoring in the density of the ligand. But now let's consider the same idea of metal ligand interaction, but in a cumulative manner. So meaning that we're factoring in more than one step. So we're looking at cumulative metal ligand interactions. Well, as it turns out, if there's literally only one step involved, one metal and one ligand involved, well, that's going to be something that it's basically, it is what it is. It's a one-step process. So you have a metal and one ligand, and that gives you the metal ligand adduct. So here I'm going to introduce to you a terminology, and that is the term beta. And beta refers to when you have an interaction that involves more than one step. Well, in this case, where you do only have one step at completely just one step, well, it turns out that beta 1 is equal to K1 because there's nothing else that can happen there. There's only one metal, one ligand interaction, and so you get the same expression. But now we can start to distinguish between beta expressions and K expressions when we have more than one step involved. So now let's consider the second ligand interacting with the metal. But let's consider it not with already a previously established metal ligand adduct. So we're not going to consider this. We're going to consider the metal by itself. And so we're going to have the metal interacting with two ligands in one go. Okay, we're not factoring in the individual steps involved. So here then, one metal interacts with two ligands, and that gives us our metal L2 interaction. So then now we can express the beta expression, which this will be beta 2. And so beta 2 is equal to the concentration of this adduct, the Ml2 compound, divided by the concentration of M by itself, times the concentration of L squared. And the squared is coming from, right, that we had two ligands interacting with that metal center. So as you can see, beta 2 is not the same thing as K2. Remember, K2 we defined previously as Ml plus L gave us Ml2. So we had this expression. And as you can see, these two are not the same. Okay. But there is a relationship there. Okay, and so where's this relationship? Well, it turns out that beta 2 is equal to the product of K1 times K2. All right, so I want to show this more obviously. So I'm going to substitute what K1 and K2 mean, and I'm showing you here that expression, where this is their K1, okay, and this is multiplied by your K2. And what we're going to do is we're going to eliminate the common terms between them. So I eliminated the common terms between them, and what you left is with this expression right here, and that expression is literally this expression here, this beta 2 expression. And so that basically gives us the overview of what distinguishes a beta versus what distinguishes the K, which Ks are single step binding processes and betas are cumulative binding processes. All right, so then how can we generally represent beta values? So here I'm giving you this expression to help you to just give us a general representation. So here we have M by itself interacting with an X number of ligands. So X, it defines how many of the ligands are bound to that metal center, are going to bind to the metal center. And that gives us the adduct MLX, where beta X is going to equal to mlx, the concentration of that, divided by the concentration of M times the concentration of L raised to the X power. Okay, so X, again, is the number of ligands that are going to ultimately coordinate to that metal center. All right, so this is our general expression for representing cumulative processes of ligands interacting with metals. All right, so with this in mind, then, now we have this general idea that there are affinity processes with one step consideration or multiple steps, so K expressions or beta expressions. Well, now let's try to factor in what are those things that are going to play a role in terms of influencing the interaction of ligands with metals. So here I want to introduce this idea that solvent plays a role. And so metal ions are, and I'm going to be a little cautious here. I'm going to put a little star here, are never really free in solution. So with solvents like water, well, the water has a capacity of binding to the metal center. And so this is something that's true, the statement here, when you talk about aqueous solutions. So in aqueous solutions, metal ions are water bound. So you put a metal ion into water, and so what you're going to get is the water binding the metal coordination sphere. Well, I'm not going to specify the number of X because it depends on what metal you're talking about, how many water molecules can actually coordinate to it. And that's something to discuss later on. So just to understand that, you put a metal ion into water, and so you're going to get a layer of water interacting with that metal center as far as a direct bond. All right, so it turns out that certain metals have a really strong interaction with water. So not only do they coordinate the water, right? All these metals have the capability of that, but not only do they coordinate the water, but they also have the capacity to induce what is known as hydrolysis. All right, so you have, just to make it obvious what I have drawn here, this is coordinated to the actual free pair of electrons in the oxygen. Well, the interaction between the metal and the water is so strong in certain cases that there is a dissociation of a proton from the water molecule. And so here we have a representation of a metal serving as a Bronsted-Lowry acid because due to its strong interaction with the water molecule, it induces the dissociation of a proton. So it donates a proton. Right? So this is actually an important property because it's not a property that all metals have in common. So let's try to distinguish this property of metals as Bronsted-Lowry acids. So here I'm giving you a list of the relative acidity in terms of Bronsted-Lowry acid definition of metals. So it turns out that alkali metal cations, so those are your metals in the first column of your periodic table. Well, those are non-acids, so they do not have Bronsted-Lowry acidic properties. Then if you move over to the second column, the alkaline earth, well, those are slightly acidic, meaning that they have the capacity to slightly donate a proton from the water molecule. Then you move into the transition metal section of the periodic table. And so in this section of the periodic table, here's where you start to increase the overall acidity of metals. So +2 transition metals, well, they are weak in terms of their acidity. But then as you increase the oxidation state, so +3, well, now you become more acidic. So +3, they tend to be moderate, and then +4 and higher, those tend to be quite strong. And then in some cases, so strong that it's virtually impossible to find a certain metal without the presence of oxygen. So an example is vanadium, where vanadium interacts with water so strongly that you get the formation of VO2 plus, right? So basically, you have complete dissociation of the protons from the water molecule because of the strong interaction. So you probably have to require two of these water molecules in order to then facilitate the formation of the oxides on the vanadium itself. So something like this, where you get like a total of 4 protons that are being released. All right, so this is called hydrolysis, and is a consequence of the interaction of a metal and its ability to be a Bronston-Lowry acid. All right, so what's going to be then important is to recognize the following, that metal ions can lower the effective pKw of water. And that's essentially what's happening here. In order for you to fine-tune the dissociation of a proton from water, you're basically affecting the pKw. And so something similar is that certain metal ions can affect the pKa of ligands. So it can affect the acidity of ligands as it can make them more dissociable or more acidic. Okay, so that's an important property when you start to look at metal and ligand interactions in an aqueous environment. All right, so again, continuing with this theme of metal ions are never free in solution, and we're being more particular here, aqueous solution. Well, ligand binding then can be seen as a competition with solvent binding. So, factoring that water can serve as a solvent then, when we're looking at a ligand interaction with a metal center, we have to keep in mind in the back of our heads that there's going to be a layer of water molecules bound to the metal. And so your ligand is overcoming that affinity in order to bind to the metal center. So here is the general expression representing that, where you have the metal interacting with water molecules, you have this incoming ligand. In solution, you form this adduct. So let's imagine that we have one adduct between the metal and the ligand, and as a consequence of this, you lose one of the water molecules from that metal ligand interaction. But when we're actually factoring in the metal ligand interaction, we actually ignored the bound water. We don't actually factor that into our expression. So if I were to ask you to give me the K expression for this one-step process, well, this would actually be the expression. We don't factor in the presence of water molecules that we know to be there because we're simply focusing on the affinity of that ligand to that metal center. All right, so keeping this in mind then, we're looking at metal ligand interactions and we're not really factoring the solvent into this equation then. What are those parameters or what are those factors that are really influencing the preference of binding? And so here, I'm going to be a little repetitive. Well, we have to, again, factor in hard, soft, acid, base theorems, which we discussed in our last lecture. And it's something that's very important moving forward in our discussion in the course. And even in your review project that you're working on, when you look at the interaction of ligands with copper, you're going to see that there's going to be certain types of typical features that you will see in terms of what type of atoms will coordinate to the metal center. So again, hard, soft, acid, base theory, which is a theory that talks about the polarizability of species. And so here, this table basically encapsulates the idea of hard, soft, acid, base theory. Well, what we're looking at is how two different metal ions, and they're different in terms of their hard and softness, are going to interact with these different halides, so these different Lewis spaces. And so what we need to factor here is the deviation in the hardness and softness. So iron 3 plus is a hard acid, and the mercury 2 plus is a soft acid. Okay. And then when we're looking at the halides, okay, well, we're looking at from left to right, we're going from something that's a hard base. And over here, then we're going to end up with something that's a soft base. Okay, so that's going to be the focus here. So remember, when we discussed hard, soft, acid base theory, well, a hard acid prefers a hard base. An intermediate acid prefers an intermediate base. And then a soft acid prefers a soft base. Okay, so that's going to be the preference of binding. So the way that we're looking at this is by looking at the K expression or the log K, which is a measure of the strength of binding. And what do we see? Well, we're focusing on iron being a hard acid. What we should expect is that the affinity of a ligand to iron will be the highest when you're focusing on a hard base. And as you can see, comparing the fluoride versus iodine, right? The fluoride is the hardest base listed here, and the iodine is the softest base. Well, you can see how the affinity scale ranges, where the fluoride is the highest, right? So that matches our expectation. And then the iota, well, it doesn't even have a measurement because it's too weak. Okay, so on the flip side, if we focus on mercury, mercury 2 plus, which is a soft acid, well, here we should expect the opposite trend. We should expect that the mercury will have a higher affinity for the iodide versus the fluoride because iodide is a soft base. And so what do we see? Well, what we see then is that comparing those two, the extremes of our what we have listed here, well, the iodide provides a log K of 12.7, whereas the fluoride is only a log K1 of 1. So clearly, the affinity of the mercury with the iodide is the highest, and that matches the expectation according to hard soft acid base theory. Right. So this is one of those factors that contributes to binding preference. But what other factors? Well, as I was alluding to earlier in our lecture, I was talking about chelators, and so certain types of chelators and the type of rings that they can form. So this is actually an important factor structurally in terms of how you can have a favorable interaction. So there's the chelate effect. Okay, what exactly is the chelate effect? Well, when coordinating through the same type of atom, a chelating ligand will outcompete, and I'm emphasizing that, outcompete a monodentate ligand version of the same type of atom for metal binding. Okay, so we're going to put this into a context so that we can understand what exactly am I saying here? Like, why is it that will outcompete a monodentate version? All right, so to provide insight, well, the types of chelators are going to be pretty specific here. We're going to be chelators that chelate by forming 5 and 6 membered rings, because these types of interactions are actually quite favorable. So just to review, when you have a 5-member ring, you have a type of interaction like this. We have, and then what else? Part of the so that's our 5-member ring. And now this is atoms. Sorry, it jumped for a second. Okay, here it goes. Two coordinating atoms, and then the unit. All right, so part of this key is going to be favored things, well, they result in unfavorable ligand distortion. Just waiting for this to catch up. Okay. All right, so just to distinguish, the chelate effect is going to be most applicable to those ligands that can form 5 and 6-membered rings. All right. So let's talk about then the thermodynamics involved in this chelate effect. Well, when we're talking about this, let's remember Gibbs free energy, right? So Gibbs, the delta G is equal to delta H, the enthalpy minus temperature times delta S, the entropy. So putting this into context in terms of this interaction of the chelators with the metal, well, the enthalpy is referring to the bond breaking and the bond formation process. Okay, and that's going to be something that we have to factor in. Also, the entropy, which, as we know, is a tendency towards disorder. So we're going to keep these two thermodynamic parameters in mind when we're talking about this chelate effect. So let's focus on a representation of this, where we're looking at an amine with this free pair of electrons. versus a bidentate version, this ethylamine, and that's going to be bidentate. So this is monodentate versus bidentate. So that's going to be the comparison here. All right, so what do we have here? What we're looking at then is the interaction between a cadmium with a methylamine. And keep in mind that the cadmium is going to be in solution. So it's going to have some water molecules that are bound to it that are going to be dissociated, some of them, when you have the four methylamines coordinated to the metal center. So let's get a little bit of insight as to the coordination chemistry here. So here you have your cadmium compound with the 6 water molecules bound to it. And you're going to have the methylamine, and there's going to be 4 of them. And that this free pair of electrons is going to coordinate to the metal center, and that coordination process will result in dissociation of water molecules. So as you can see on the right, you have a representation of 4 methylamines. And so I just arbitrarily chose where they bind, and you're going to be left behind with 2 water molecules. Okay, but let's look at the overall net of the system. So you have 4 methylamines, and that results in 4 water molecules becoming dissociated. And so here you have your K expression. So this actually should be a beta expression as beta, because this is going to be a cumulative process as I've represented here. So this is 3.3 times 10 to the 6. Okay, so it's something that's a favorable process for the formation of the product. But let's compare this to a chelator version of this process. And so we're looking at the ethylene diamine. Okay, so again, we have our starting compound, and then we have our ethylene diamine. Which uses this free pair of electrons on the nitrogen. So these pairs of electrons, where you're going to have them interacting with that metal center and then facilitating coordination to the metal center. All right, so here's just a representation, and I just chose where they bind. We have 2 of those ethylene diamine coordinated to the cadmium, just like in the previous example, we had 2 methylamines coordinated to the metal center. All right, so you still have the same result where you're left with 2 water molecules. So in this overall process, 2 ethylene diamines result in the release and the dissociation of 4 water molecules. But interestingly enough, the if you look at the beta expression here, the beta value here, the value of that interaction is significantly different. Now you have 4 times 10 to the 10, right? So 10 to the 10. And before, when we were looking at this, with the monodentate, it was 10 to the 6. So the chelator provides several orders of magnitude higher affinity to that metal center. So the question is, why is that happening? Why do we have this difference? All right, so well, what's actually happening in terms of the what's binding? So let's clear this up a little bit. Let me just clear this up a bit. So when we start off, right, with our starting compound, with either the monodentate or the chelator, it doesn't matter. What we have are cadmium oxygen bonds, right, from the 6 water molecules. So we actually have 6 of these that are present in our starting compound. And then at the end, we're going to have 2 cadmium oxygen, and we're going to have 4 cadmium nitrogens, right? So what we have is that we broke 4 cadmium oxygen bonds so that at the end, we form 4 cadmium nitrogen bonds, okay? So that's what's happening, at that, like, really, at the molecular level, at the atomic level, as far as what's actually being broken and what's actually forming. And the same thing is happening for both of these reactions. So in terms of bond formation and bond breakage is identical for both. Okay, so it can't be that's contributing to the difference in affinity. Okay, that's not what's likely happening. But what is contributing is the entropy of the system, where when you're looking at the monodentate version of this reaction, on the left side, you have 5 molecules. And then when this exchange of ligands occurs, you still end up with 5 molecules. So your net here is a net of 0. There's actually no change in the total number of molecules from the left to the right. But when you're looking at the chelator version, you have 3 molecules initially, and then you end up with 5 molecules at the end, such that your net overall is going to be an increase in the number of molecules in solution. And so now you have an entropic gain, okay? And so this seems to be driven by entropy. Well, let's look at the actual values of enthalpy and entropy. Well, when you look at the enthalpy, and remember enthalpy here is a measure of the bond breakage and the bond formation, well, they're virtually identical. They're not going to be spot on, but they're basically identical because they have the same number of bonds broken, the same number of bonds formed. But the entropy is quite different. And again, that has to do with the net change at the end of how many molecules either increased or decreased, in this case, increased in the case of the chelator. And so that difference in entropy is the reason why the delta G for the B reaction is even lower than the delta G of the A reaction. Okay, both of them are favorable, but one is even more favorable. All right, any questions about that? Any doubts that you have about this? Okay. All right, so the last thing, and even if I don't finish, I'll finish it when I return. We're going to talk about this idea of metal ligand interactions and how they can stabilize the oxidation state of a metal ion. All right, so that can also be something that contributes to the preference of a metal ligand interaction. So when we're defining this idea of the oxidation state, and we're talking about this movement of electrons, let's review this concept. So oxidation and reduction, where an oxidation is the loss of one or more electrons, and a reduction is a gain of one or more electrons. So when you're talking about a process that's involving movement of electrons, you will have a coupling of oxidation and reduction. This is referred to as oxidation reduction or redox. And so the thermodynamics is going to be driven by this process of the number of electrons that are involved. So you have this expression, delta G equals to negative NFE. So let's break down this equation here, where the N is referring to the number of electrons that are involved in the system. The F is Faraday's constant, and the E is a very important parameter, is the electromotive force. So that basically defines the potential energy for the movement of electrons or the movement of charge, such that then when you're focusing on a redox process, for it to be thermodynamically driven, these are the parameters that you want to meet, where your electric motive force will be something that is positive. Okay, so let's imagine that this expression here is positive, so that then your overall system will end up being negative, and that would define something as being spontaneous or thermodynamically variable. Okay, so that's something to keep in mind when you're thinking about what's enabling the movement of charge. So let's look at this from the perspective of one metal here. So here I'm looking at the process of the reduction of iron. And so we're looking at iron 3 plus, and I would note to you, that's why I put this note right here, that when you look up tables in textbooks or like in the literature, you always have these type of processes written in terms of a reduction, in terms of a gain of electrons. So that's the typical way that the field will represent these type of processes. Well, let's just focus on the reduction of iron from iron 3 to iron 2. So here I'm showing you this reduction, the gain of 1 electron to give me iron 2. And we're looking at this in an aqueous context because much of what we're talking about has been in an aqueous context. And so for this particular reduction process, the electric motive force is quite positive. It's 0.77 voltage. And so this is a parameter that in terms of electrochemistry is relative to what electrode is being measured. So the typical electrode that you compare to is the standard hydrogen electrode or the normal hydrogen electrode. So that's why I'm reporting this number very particularly. And also the parameters involved in that measurement, where there's a pressure of 1 atmosphere, temperature of 25 degrees Celsius, and also a pH of 0, which means that this condition is acidic. And so I'm emphasizing acidic because if you were to try to do the same reaction at neutral pH or even at basic pH, this reaction will lead to a process that actually results in precipitation of the metal. So oftentimes when you're looking at metals being reduced, you're going to be given a value that's going to be in the acidic range in order to look at the species in solution. All right. So anyways, so what is this actually telling us? Well, based on this value of positive 0.77 voltage, well, that means that this reduction is a favorable process. And so in a reducing environment, ligand-free, so uncoordinated iron, will have an oxidation state of 2+. The thing is that we live in an oxidizing environment. And so in our oxidizing environment, iron 3 is actually what dominates. So obviously the environment is what's influencing this. So I emphasize that because coordination chemistry can really influence the oxidation state of a metal. So here is the same reaction that I was just looking at, the reduction of iron 3 by 1 electron to form iron 2. But then here we have a chelator, which is bidentate, that can coordinate the metal center. And so here we're looking at the same process of 1 electron reducing the iron 3 to iron 2. And then we see here that this electromotive force is extremely negative. And so the interaction of that particular ligand coordinated to that metal will actually move the thermodynamics of whether the metal center can actually be reduced. So what's happening here is that the ligand is actually stabilizing the oxidation state of the metal so that it remains iron 3, because now you have something that is quite negative, and therefore it would dictate that that reduction process is not thermodynamically favorable. All right, so I'm going to stop here so that I can continue just the last bit of this when I return from from my conference. In the next lecture, Aixa will be talking to you about isomerism. So another theme in coordination chemistry, but I will finish with the few slides that remain here after the when I return. All right, and everyone, if you don't have any questions, well, have a great rest of your day.
Professor, I couldn't
Yeah.
find this specific presentation in the web page, so I don't know if.
Well, it's there, but I can see if for some reason it didn't show up when but it's there when I last checked.
Okay, well, if I can't find it, well, I'll just let you
Yeah,
know.
just let me know and I'll see what happened. Okay,
Okay, thank you. Have a good one.
you too.
Profesor,
Sophia,
¿podemos hablar un momento?
yeah, I can. I was going to speak to Sophia if she's still available. Who's speaking to me?
Ian.
Bye,
Okay.
Professor. Have a good day.
All right, bye, everyone. You too. Ian, let me see if Sophia's. I see her name, but I'm not sure she's there. Sophia, are you there? Yeah, Ian, are you there?
Sí,
Okay, we'll go ahead and talk. I'm gonna remove her from here. Okay. All right, so what's up?
ok, pues rapidito, ¿verdad? Yo sé que la semana pasada yo le había enviado la excusa de que iba a estar de viaje y demás. Yo tenía en mis planes, ¿verdad? Llevarme la computadora y adelantar los trabajos, ponerme al día con las clases. Pero en el laboratorio
Un
donde nos
momento,
estábamos
Ian.
quedando,
Perdón. Oh,
ya,
just